Welcome to this explainer. Okay, imagine you've got this massive bank account balance. We're talking millions of dollars, sitting right there in your name, but you've completely forgotten your PIN. The wealth is physically there, right? But it's utterly inaccessible when you actually need to spend it. Well, that incredibly frustrating scenario is exactly what we face in agriculture when we're dealing with raw biochar and its core nutrients. Today, we're diving into a really fascinating scientific puzzle: the fate of nitrogen and phosphorus during the intense heat of pyrolysis.
Here's how we're going to break this down today. First, the great biochar paradox. Second, nitrogen, the escape artist. Third, phosphorus, the shapeshifter. Fourth, the temperature trade-off. And finally, rethinking biochar for agriculture.
All right, let's jump right into section 1, the great biochar paradox, or what is essentially a nutrient illusion.
So, we have to ask the big question right up front. Is biochar actually a good fertilizer? I mean, think about it. We take nutrient-rich organic waste, stuff like manure, digestate, or crop residues, and we bake it in an oxygen-limited environment to create biochar. It makes total logical sense to assume that the resulting black carbon is packed with the exact same fertilizing power as the raw material we started with. But, as we're going to see, the science tells a very different, and honestly much more complex, story.
That assumption completely fails because we really have to separate two distinct concepts here: total nutrients versus plant-available nutrients. Total nutrients are just the chemical elements that are physically present in the biochar. That's your locked bank vault. Plant-available nutrients, on the other hand, are the fraction of those elements that are actually soluble enough for crops to absorb and eat. That's the gold you can actually spend. And when it comes to biochar, having a high total nutrient concentration absolutely does not guarantee high plant availability.
When the intense heat of pyrolysis hits, our two vital macronutrients react in completely opposite ways. It's kind of like watching two contrasting characters in a disaster movie. Nitrogen completely panics, volatilizes, and actively escapes the scene. Phosphorus, on the other hand, stays behind and hunkers down. But to survive that extreme heat, it ends up completely changing its chemical identity.
Which brings us to section 2. Nitrogen, the escape artist. 50 to 90%. Just let that sink in for a second. That is the staggering amount of original nitrogen that is completely lost during typical pyrolysis temperatures of 450 to 700 degrees Celsius. See, in the raw biomass, nitrogen is comfortably housed in proteins and amino acids. But the second you apply the thermal stress of pyrolysis, those organic bonds literally just crack apart.
So where does all that escaping nitrogen actually go? Well, the vast majority of it migrates right into the gas phase. Under that intense heat, the chemical bonds break, transforming the nitrogen into volatile gases. We see a massive release of ammonia, and as the temperatures climb even higher, it starts generating highly toxic gases, like hydrogen cyanide, before eventually just becoming inert N2 gas. Another chunk gets captured in condensable liquid bio-oils, leaving only a really small fraction behind in the solid char.
But get this, here's the real kicker. For that tiny bit of nitrogen that does actually manage to stay behind, it doesn't stay in a form that plants can even use. It undergoes a process called graphitization. Basically, the nitrogen gets permanently trapped in these rock-hard, highly stable heterocyclic structures. They're complex chemical rings that act exactly like a biological vault. They are completely inaccessible to plant roots and most soil microbes. So you might have total nitrogen on paper, but you have practically zero available nitrogen in the soil.
Let's move on to section 3, phosphorus, the shapeshifter.
Now, unlike nitrogen, phosphorus is not volatile at your standard biochar temperatures. It actually doesn't evaporate below 700 degrees Celsius. Because of that, a massive 70 to 95% of it is retained right there in the solid char. And because the carbon mass is burning away while the phosphorus stays put, the total concentration of phosphorus actually goes up. But here's the catch: it survives by completely shifting its chemical speciation. It transforms from labile, easy-to-absorb organic forms into highly stable, inorganic mineral forms.
The science proves that temperature dictates literally everything about this shape-shifting behavior. If you look at lower temperatures, say between 300 and 500 degrees, you maintain a higher bioavailability because the phosphorus stays in somewhat labile forms. But as you push the heat over 500 to 700 degrees, the overall concentration of phosphorus might go up, but its immediate plant availability absolutely plummets to less than 10%. And here is the ultimate chemical climax for phosphorus, apatite crystallization. At those really high temperatures, the phosphorus reacts with calcium, magnesium, and iron in the ash. It builds this highly insoluble crystalline mineral shell around itself, forming minerals like hydroxyapatite or whitlockite. Going back to our forgotten bank account pin analogy, the phosphorus is physically there in the soil, no doubt about it, but has essentially locked itself away behind an impenetrable mineral wall.
So that brings us to Section 4, the temperature trade-off, carbon versus nutrients. This right here reveals the ultimate frustrating catch-22 of biochar production. Think about it. If you pyrolyze at a low temperature, like 300 to 400 degrees, you preserve those plant-available nutrients. The nitrogen hasn't completely gassed off yet, and the phosphorus hasn't crystallized. But your carbon stability is super low, meaning it's not going to sequester carbon in the soil for very long. On the flip side, if you crank the heat above 600 degrees, you get incredible aromatic carbon stability that's great for fighting climate change, but your nutrient availability drops to practically zero. You just can't easily have both.
All right, finally, Section 5, rethinking biochar for agriculture.
The good news is, brilliant agricultural engineers are actively hacking this system as we speak. Instead of viewing biochar as this finished fertilizer right out of the oven, we need to treat it as an incredible, porous sponge. Step 1, we aim for a compromised temperature window, usually around 400 to 500 degrees. Step 2, we charge that sponge after production. We do this by co-composting it or soaking it in liquid digestate, which allows organic acids to slowly dissolve those locked-up phosphorus minerals. And step 3, we actively capture that escaping ammonia gas from the pyrolysis process and route it right back into the biochar to reload the nitrogen.
So here's the really powerful takeaway from all of this. Raw biochar is phenomenal for improving soil structure, for retaining water, and for sequestering carbon. It is an amazing foundational soil function amendment. But because of the extreme chemical transformations that nitrogen and phosphorus go through during pyrolysis, it is absolutely not a silver bullet complete fertilizer on its own. It requires smart management and post-production enrichment.
Which leaves us with this final, provocative thought. As we scale up biochar technologies globally, how do we perfectly balance the vital, long-term necessity of sequestering stable carbon with the immediate, pressing need to provide accessible nutrients to feed a rapidly growing planet? It's a massive engineering and agricultural puzzle, and honestly, it's one that's going to define the future of sustainable farming. Thank you so much for joining me for this explainer. Keep asking questions and keep exploring.